Okay, so now we're going to start really progressing with the set theory. We're making our way towards computable enumeration, computable enumerability, but we're really going to be doing set theory for a little while, and you'll see there's computability theory kind of peppered around as we do the set theory. But I'm building towards a result that is as set theoretical as it is computational. So we really kind of need to do it this way, I think. So recall, in case you watched that video that I just made a long time ago, that the Cartesian product, or just the product of A and B, is the set of all A, comma B, such that A is in A and B is B is in B. It's the set of all ordered pairs from this from A and B. And you can do the same thing with multiple sets. I can say A cross B cross C is the set of all ordered triples A, B, C, such that A is in A, B is in B, and C is in C, and so forth. Now, the reason I needed to define that is because I really want to define functions formally. And in order to define functions formally, I need to define relations formally, which I need later anyway. So definition. This is sort of this is a definition, but it's not quite sufficient to every case. But it's good for starters. So let A and B be sets. A relation from A to B is a subset, I'll call it R, of the Cartesian product A cross B. So, and also, well, okay, no. Yeah, so that's that. A relation is any subset of the Cartesian product of two sets. But, I mean, it does, well, okay. So if x and y are in the relation, then we say x is related to R, or if the context isn't clear, x is R related to y, or just x is related to y. And sometimes write that x is less than or equal to y. So if A and the B are the same set, by the way, then really what I have is a relation as a subset of A squared, A cross A. Then I call a binary relation. On A. And that's the reason that this definition here of a relation from A to B is not really the complete definition of a relation. It's kind of the most typical one. But if I define a relation as a subset, I can, relations that are on, products of the same set are called, binary relations or tertiary relations, right? If R is a subset of A cubed, that's A cross A, then I can say, it's a relation between three different things. It's a trinary, tertiary. I'm not really sure which. And I can even have R as a subset of X, right? If I can even have unary relations. Right? There are unary relations that are really valuable, and sometimes I'll reuse those. And basically, the most general way to do it actually is not to say, is to denote it basically. If X is in R, and R is interpreted to be a relation, then I say like R of X to say X is in R. So if I write R of X, this is basically the statement. X is related. X is in R. X is related in whatever way I'm talking about. So relation is a really general definition. Any subset of any set can be considered a relation, but it's the place to start. So let's do some examples to make this less abstract. So first off, how about something really familiar to everybody? R equals the set of all x, y, such that x squared, well, maybe I should say in R2. So this is a binary relation. It's the set of all x, y, and R2 such that x squared plus y squared equals 1. This is the unit circle. The set of all of the xy pairs in this relation constitutes the unit circle. So remember, relations are subsets, and as a subset, it's really the unit circle as a subset of R2. Let's try that one more. That's still pretty bad, but you get the idea. So if this is the set R, it's a relation. And so if x squared plus y squared equals 1, then I could say x, and x is related to R in this way, that it's on the unit circle. So this circle is a subset of R2. Another example maybe, how about less than or equal to? This is a relation on n, the natural numbers. The natural numbers are 0, 1, 2, 3, ... 0 is only there if you care, if you want it to be. It's not there if it's not convenient for it to be. So I mean, yeah, it's less than, right? If 1 is less than or equal to 2, then that's what I'm really saying. 1 is related to 2 in this way, that it's less than or equal to. And so in particular, I can see less than or equal to as a set. It's the set of all, like, it's hard to define it explicitly as a set, but it's the set of all pairs of natural numbers where the first entry is less than or equal to the second entry. So in particular, it's got like 0 and 0, right? It's got 0 and 1. It's got 3 and 4, and so forth. It's a big infinite set, but it's a relation. In fact, if I view it as a relation R, that is a binary relation on R2, then I have this. So here's R2 again. And so it's the set of all xy such that x is less than or equal to y. So really, here's the line x equals y. Whoops, let me try that again. So here's the line x equals y. And that's a relation too. Equality is a relation. Equals is also a relation. On whatever, anything really, anything you have the equality defined on, you can look at equality as a relation, and so it's all of the xy such that the second entry is bigger than the first. So it's all of the set x such that y is greater than x. So it's really this top chunk of the. So you can see the relation as basically this half of R2 is the relation less than or equal to. Less than or equal to is a set. Every relation is a set. And so you're getting the sense, hopefully, that you've used relations your whole life. You just haven't known it yet. You haven't seen it in this way. You haven't seen it explained this way. And in fact, we can always define the domain and range of at least of a binary relation. Go ahead and say it like this. So for relations between two sets, A and B, i.e., we can define the domain of R to be the set, I'll denote it dom R or whatever, is equal to the set of all x in A such that xy is in R for some y in B. So it's the set of all things on the left side. It's the set of all stuff on the left side of this pair. The set of all left entries of pairs. And similarly, the range of R it's exactly the same thing, but for B. It's the set of all y in B such that xy is in R for some x in B. X in A, excuse me. So you can see they're pretty much the same definition. So that's relations. Hopefully that makes sense. And why am I talking about relations right now? Because a function is a special kind of relation. So a function is a special kind of relation. So I really defined relations just now because I want to formally define what a function is. So here's the definition. A function, sometimes called a mapping, from A to B, is a relation f from A to B. So what I mean by that really is a function really is a subset of A cross B, such that what are the special properties that need to be true in order to have a function? Well, there's two essential elements. Number one is that everybody knows that this circle here is not a function. It doesn't pass the vertical line test as you're taught it in high school or whatever, right? It doesn't pass the vertical line test. What does that matter? What's the point of this? Who cares? Well, the reason is that it's a function. I want to think of it as like a box. I want to think of it as like an input and an output. So I put an x in the box, and I get a y out. I want to think of it as an input and an output. So how do I think of a relation as like an input and an output? Well, I basically need to make sure, one, that I only get one thing out of the box every time. And that's why the vertical line test is a thing. Because right here, here's an x, and there's two y's associated with it. Both of these are elements of the relation. So if I want to think about this circle as like an input and an output, I'm screwed because, you know, I put an x in my toast. I put a piece of bread in my toaster oven. It doesn't spit out two pieces of bread. It spits out one piece of bread. There's one output per input, and that's not the case for the circle. So the circle is not a function because in order to think of it as like a box, right, like this, it needs to have just one output per input. And then the other important thing is that its domain is the whole set, but that's really kind of a formality. It's really the second thing I'm going to write here. So the first thing is kind of more of a formality, which is that the domain of f has to be equal to A. Kind of a formality. If the domain isn't A, then I can just express the domain as the set of all things that I can plug into. The bottom line is that if I write that f is a function from A to B, then I should be able to plug in anything I want from this set A. So that's why that is. So that's really what this means is can plug in anything. And then two, if I want to basically write down that observation I made before. So if xy is an element of f, remember f is a subset fundamentally, and xz is also an f, then y equals z. So this is a way to say that one input gives you one output. It's also a way to kind of express the vertical line test in letters and words. One input, one output. And obviously I'm putting these things in quotes because it's kind of a choice to interpret things as inputs and outputs. But that's the idea with a function. So notation. If I say f with a colon and then A and then a line and then B, B. This reads f is a function from A to B. So that's how this reads. And so if I'm just kind of specifying a function kind of in the abstract arbitrarily without any kind of special rules, I'll just define f to be from A to B. So the domain is implicitly all of this. And this right here, you know, the range is not necessarily equal to B. right? So I need to give a name to B, which I will in a second. B here is called the codomain. So the range is the set of all the y's such that there's an a that maps to this, or an a such that x, y is an f. But that's not necessarily all of B. So B itself is called the codomain, which is a bigger set than the range. And then the stuff you're more familiar with, if x, y, the pair, is in f, then of course you never write this. We write f of x equals y. Right, this is what you write instead. But this is the same. This actually fundamentally what this means as a statement is that x, y, the pair, is in the function, because the function is a set. Because everything in math is a set. Fundamentally, everything in math is always a set somehow. You just don't know how yet. So that's the abstract, that's the technical definition of a function. Let's do some examples. So here's an example, just to connect back to computability theory. The transition function of a Turing machine. Right, if m equals sigma q delta is a Turing machine, whoops, then delta is a function. Delta is a function. It's a function specifically. I've written this down before you, but you had no idea what I was writing back then. What's the domain of delta? It takes a symbol and a state as an input. So its domain is sigma cross q, and its codomain is sigma cross q. It spits out a new symbol and a new state, and then it also spits out a direction, which I kind of looked at as an integer, as -1, 0, or 1. And you can see very clearly from this, I think, that the codomain is not the same thing as the range. Why should it be the case that every single possible symbol, state, direction has to be the output of something? It doesn't. The range is very different than the codomain here. This is the codomain. It's the set of all symbol, state, direction pairs, but not every symbol, state, direction pair needs to be, the output of something. That doesn't necessarily have to be. However, it does have to be the case that if I put in a single symbol and a single state, then I get out a single instruction. So let me write that down. So the fact that delta is a function and not just a relation is what makes the behavior of M deterministic. Right? If I had two outputs, if for instance, like, if delta of sigma q equals lambda q d, and delta of sigma q equals like gamma r d, right? And these weren't the same, which would be fine for a relation. Remember, relations are just arbitrary subsets. So if this was a relation from here to here, then I could have something like this, and then it would be kind of unclear. What does the machine do when it sees this symbol in this state? Does it do this, or does it do this? So the fact that this is a function and not a relation is extremely important, because it's what makes M a deterministic machine. It's what makes M deterministic, and in fact, our definition of a non-deterministic Turing machine, which is how we'll decline the class NP, and non-determinism is a giant part of this of computability theory. Later, we will define non-deterministic machines by simply relaxing the requirement that delta be a function. to simply being a relation. So this is how actually we're going to define non-deterministic Turing machines. We're going to say delta is no longer necessarily a function, it's just a relation. And we'll have to talk about like how to think of that. There's a lot to think about there once we get there, but that is how we're going to define non-deterministic Turing machines later. And of course, yeah, when I write, keep in mind, when I write this right here, what that really says is that, what that's really claiming is that sigma q, this pair, sigma q comma lambda q d, is an element of delta. Delta is a set. It's the set of all things that look like this, or it's not all things look like this. It's a set of things that look like this, and that's really what this is covering up. So I think this is a good place to break the video. In the next video, I'm going to define one-to-oneness and onto-ness, and that will put us in a good position to define cardinality, which is kind of the current immediate destination for us.